So today we have a reasonably dry chapter, unfortunately, but it's important to look at how being a science actually affects psychology and what it means to study the human mind in terms of it being a science. So, all science has two basic core beliefs. First, that the universe operates according to certain natural laws. Now, if this wasn't the case, science would be virtually useless. The universe has to operate according to these laws, because if the universe is essentially random, then there's no way that we can discover and understand uh, how it works. Okay? And that's true of psychology as it is of physics. And we have to believe that these laws are discoverable and testable. Now, it's important to notice that we don't have to know what these laws are. We just have to know that they exist. Okay? And we don't necessarily have to be able to discover and test them with the technology that we have now. We may not have the technology to be able to discover and test these scientific natural laws. In fact, for thousands of years, we didn't. There was no way we could have discovered, for instance, quantum physics before the technology of the 20th century. It would not have been possible. So, as we advance through our technology, these laws become more discoverable and more testable, and we can get closer and closer and closer to the truth. The scientific method uses a couple of different ways of determining logic. We have inductive reasoning, we have deductive reasoning, and we have what we refer to as hypothetico-deductive reasoning. And science really uses this hypothetico-deductive reasoning as a combination of the first two. So let's look at exactly what those are. Deductive reasoning uses the general principles to apply to a specific situation. So we can look at it and say, if I let go of an object, it's going to fall. Therefore, if I hold my pencil up and let go of it, it will fall. We have a general observation, and then we apply that general observation to a specific situation. Inductive reasoning is the other way around, using specific examples to draw general conclusions. We use this method when we say, all right, if we test 500 million things by letting them go and seeing if they fall, then we can determine then that things fall. And we can examine these specific instances and draw general conclusions from them. Okay? Children are great at inductive reasoning. They drop things all the time in order to accumulate a number of specific instances from which they can draw general conclusions. That is, if I drop my bowl of SpaghettiOs, it will fall and make an enormous mess. This is a nice little graphic to look at the reasoning in the scientific method. Although under deductive reasoning it says it starts with a theory, we generally say that it starts with a hypothesis, the same way hypothetico-deductive reasoning begins. There is a difference scientifically between a theory and a hypothesis. The inductive reasoning and the hypothetico-deductive reasoning categories actually give a more appropriate look at a theory, but we'll talk about that here in just a moment. The modern scientific method has a series of very clearly defined steps. And the first of these is to make general observations. Now, these aren't scientific observations, but just things that you notice in the world around you. There was a fairly famous experiment where we did an actual experiment on the concept of beer goggles. Now, beer goggles is the concept that, and if you'll forgive the slightly misogynistic aspect of it, the more you drink, the prettier she gets. That's the concept of beer goggles. So we make this observation that people believe beer goggles exist. They think that when you drink, it impairs your judgment, so you become more attracted to less attractive people. So we develop a hypothesis based on these observations, and that's our next step. A hypothesis is a testable, falsifiable prediction. Falsifiable means that our prediction can be proven wrong, not right, right? This slide is actually wrong. You can never prove that your prediction is right, right? A hypothesis can never be proven right. The best that we can do is show that it is not wrong. Okay? A lot of our hypotheses will be proven wrong. So we develop a hypothesis based on beer goggles and say the more you drink, the more you are attracted to less attractive people. That's our hypothesis. It's not a theory, remember. With a hypothesis, we're making a prediction about what we will discover. The next step in the scientific method is to test our hypotheses. And in order to do this, we have to generate testable definitions for things. For instance, we want to know how attractive someone is, so we can actually create a set of definitions for an attractive human. And we actually have. We have a scale of 1 to 10 of an objectively attractive human being, based on other scientific papers that have been published determining what people actually find attractive, not what they say they find attractive, which is actually a very different thing. And then we look at going into a bar, for instance, and we start observing relative attractiveness of the people in the bar. We keep track of how much they drink. We keep track of what they're drinking. We keep track of who they appear to be attracted to, who they're talking to, who they leave with. All of these things are part of our hypothesis testing, and it's extremely rigorous and extremely detailed, so that we eliminate as many of the variables as possible and take as much into account as we possibly can. Now, once we've tested our results, we're able to analyze our data and come up with some conclusions. And from that conclusion, we can begin to build a theory. Now, our theory is what we believe to be the laws that govern behavior, these testable laws of the universe. Our theory describes what we think those laws are, not simply a prediction or a guess, but a reasonable conclusion drawn from the available evidence. That's what a theory is to a scientist, a reasonable conclusion drawn from all of the available evidence. Now, a theory, like a hypothesis, is never considered right. What it is considered is the best possible conclusion that we can draw. You are welcome to prove theories wrong. You should. We like it when you prove theories wrong, because when you prove a theory wrong, we come closer to the truth. You cannot simply say, oh, well, it's just a theory, we can throw it out, because that's not what a theory means. The last steps in the scientific method is to publish and verify your results. Because one experiment is rarely enough to say, oh, well, that's how it is all over the world, particularly when you're looking at cultural context within psychology. So it's important that we publish our evidence so that other scientists can look at it and determine whether or not we may have made a mistake, whether or not there was something that we forgot, something that we missed, something we didn't think of. All of these things are important in publication and replication. If you don't publish, then you haven't added to human knowledge. You can't keep your secrets to yourself in science. It's important that we make sure that everyone knows what we've learned. And so these are sort of the steps in the scientific method, all the way up to publication and replication of our study to make sure that we've done everything right. So, is psychology a science? A lot of physicists will actually say no. They argue that it's not a science, and that's simply because it's such a soft science, because we can't say, oh, well, a psychology experiment discovered this, therefore every individual will do this. That's not the case. It's never the case with people. So with psychology, we say that it's a very soft science, but because we use the scientific method, because we demand rigorous, verifiable evidence before we form these theories, psychology is a science, even if it is a fairly soft science. Okay? So psychology uses the scientific method. Pseudopsychology, okay, does not use the scientific method, and pseudo means almost or it resembles. Okay? Pseudopsychology does not use the scientific method, and sometimes we use the term armchair psychology when we talk about pseudopsychology. We can talk about, for instance, parapsychology, where people are looking at being able to see angels and see ghosts and that sort of thing. We can look at astrology. We can look at, for instance, the anti-vax movement, right? Now, there are and have been scientific studies actually examining times when people have claimed to see ghosts. There have been scientific studies on astrology. There have been scientific studies on vaccination and autism. And what we've shown is that there is no evidence that people actually see ghosts. Now, it's very hard to prove a negative. We cannot prove that they didn't see a ghost. But we can show that there's no evidence that they actually did. Okay? We have shown that astrology is guesswork. Okay? Astrology is accurate as often as chance would allow, which is not very much. All right? Most astrology, particularly the stuff that you read in the newspapers, really is so vague and so general to anyone. What we're looking at when we look at astrology scientifically, we're looking at things like natal charts, where you can spend literally hundreds of dollars to have an astrologer generate the full chart of where all the stars and planets were on the day of your birth in order to determine something about your personality. And it doesn't work. Okay? And things like, for instance, the anti-vax movement. Well, people don't want to vaccinate their kids because it supposedly causes autism. In this case, Andrew Wakefield's famous experiment where he showed that vaccines cause autism, he falsified his evidence, and he was actually removed from the scientific community. He can't publish anymore because his breach of trust was so egregious. And there have been hundreds of experiments that showed that vaccines do not cause or even affect autism rates. Okay? It has no bearing whatsoever. So, pseudopsychology does exist, and pseudopsychology exists a lot in mainstream culture. That does not necessarily mean that there have been no scientific studies done on these things. But what it does mean is that you have to be very careful. You have to verify where you're getting your evidence from. So how do we actually conduct our research when we're looking into examining a scientific principle? We have to develop an experiment. We have to develop a hypothesis, and we have to begin testing that hypothesis. And part of the beginning of testing a hypothesis is looking at what our variables are going to be. The first thing we have is an independent variable. This is the variable that you're actually going to manipulate as the scientist, as the researcher. You manipulate this variable. You change something about the people or the subjects of your experiment. The dependent variable is what you measure usually at the beginning and at the end of your experiment. You don't manipulate the dependent variable. The dependent variable depends on the independent variable, which you do manipulate. Let's start looking at whether or not you can determine the independent and dependent variable. This is just some practice. With Dr. Smith examines how daily exposure to a sun lamp, either 1 hour of exposure or no exposure, impacts people's depression levels in wintertime. The independent variable then is exposure to a sun lamp, because this is actually what Dr. Smith is manipulating. The dependent variable then is depression levels in the wintertime. This is what he'll be measuring, usually at before and after the experiment actually begins. So the second one, does the age of a child, either 4, 5, or 6, influence how well the children read? All right, I actually need to rewrite that. Does the age of a child influence how well the child reads? The independent variable here is the age of the child. And while you're not actually manipulating that, so we wouldn't actually call it an independent variable, that is essentially what's being manipulated in the experiment. And then how well the child reads is the dependent variable. That's what we're measuring. And then the amount of time reading your textbook, does that influence how well you will do on your exams? And in this case, we manipulate how much time you read in your textbook. So that's your independent variable. And we measure how well you will do on your exams. So that's your dependent variable. When we're looking at what variables we're going to use, it's important that we be able to define those variables. Words in English, words in any language really, can have multiple definitions, and they mean different things to different people. So it's very important that we actually define these variables in a very specific way so that when other scientists want to replicate our research, they're capable of doing so. So we use what we call an operational definition. Right? An operational definition is a specific, measurable definition of the words we use when we define our variables. Right? So when we want to define, for instance, exam performance, right? How do you define how well you've done on your exams? Well, there's a bunch of different ways you could do that. You could define it as the number of questions you got right. You could define it as the percentage of questions you got right. You could define it as the number you got wrong, the percentage you got wrong. You could define it as the number of questions you skipped. You could define it as the number of words on your essay exam. You can define it as the letter grade that you got. You can define it as how long it took you to complete the exam. There are numerous ways to define performance on the exam. So it's necessary and important that you actually specifically define what you mean by performance on the exam. It's also important that you actually define what exam you're using so that other researchers can replicate, preferably using the same design. Okay. I want you to just think about this, how you would specifically, operationally define some of these words. And remember, there are hundreds of ways that you could possibly determine what these words mean. Operational definitions are critically important. Operational definitions have been shown to be critically important. There was actually a very famous experiment. It made its way all the way into the mainstream media, although the mainstream media missed the point. The study was done on domestic abuse and in particular sexual abuse of children. And it was what we refer to as a meta-analysis. That means that instead of actually sitting down and doing the research the way you might think of it in a laboratory and whatnot, instead they took a whole bunch of papers that had been published on the topic and condensed them down into a single paper to get a broad overview of sexual abuse of children. And what made it into the media and what made it so famous was that they suggested that close to 95 to 98% of all children were sexually abused by their parents. And the media, of course, blew this up, and everybody was saying, oh, well, I wasn't. And you're right. They were absolutely right. They weren't. What had happened was, and this was actually in the very last paragraph of the paper, that the media and indeed many scientists even didn't get to reading this last paragraph because they were so upset by what the conclusions drawn were. The last paragraph said that their operational definition had to be so broad because of all the other operational definitions they were using. Their operational definition of sexual abuse had to be so broad that, for instance, seeing your parent come out of the shower or walking in on your parent in the bathroom was considered sexual abuse of a child. Now this happens. If you live with someone for 18 years, eventually you're going to see them come out of the shower. Eventually you're going to see them drop a towel, right? This happens. It's not sexual abuse, it's not scarring. Most of us just go, "Oh, Dad, come on, man," and walk out of the room and it's fine. We're not scarred by this. We forget it. So, but this is what this experiment was really about. It wasn't about sexual abuse of minors. It was about operational definitions and why we have to be so careful when we define our variables. So, absolutely, be careful when you define your variables. Be extremely specific so that everyone understands truly what it is that you're talking about when you get into your operational definitions. Once we have our independent variables and our hypothesis settled in, we have to start looking at data collection. And data collection requires that we first have participants. When we choose participants, we have to start looking at how we define how we're choosing our participants. And we can begin by looking at what population we want to examine. Now, it's easy to say, oh, well, I want to study humans. Good, fine. That's a population, and that's a perfectly acceptable population, and we do, in fact, use it. We can also use other populations. We can use the population of college students. We can use the population of high school footballers. We can use the population, any population that we choose to use. But the point is, a population is usually too large for us to study everyone in the population. There is no way you could study every human alive. By the time you got through with the ones that you were using, a whole bunch would have died, a whole bunch would have been born. There's no way for us to use that population. So usually, when we're looking at defining our variables, we want to look at a sample. And a sample is a portion of the population that is selected for study, often a relatively small portion of the population. Between 50 and 100 is actually quite a normal sample, even for studying all humans. One of the biggest samples that's used on a regular basis is from the Gallup Company, and I'll come back to them later. But the Gallup Company uses a sample of about 5,000 individuals to study both America and the population of the world. When we select our sample, we usually ideally, we look for random selection. All right, we randomly choose a sample from the population. That means every individual who is part of the population has an equal opportunity to be selected. Ideally, we have random selection. That's almost never the case. Instead, what we're going to have is an attempt at random selection that is confounded a little bit by sampling biases. And unfortunately, sampling biases are a part of choosing a sample, almost no matter what population you're using. We can have a whole bunch of different sampling biases. For instance, a real area bias is extremely common, particularly in psychology experiments, where we look at, okay, well, I want to study humans, but what I have available to me is college students in the East Texas area. That's my real area bias. I don't have the finances, I don't have the mode of transportation, I don't have the resources to study people in China and Afghanistan and Russia and Poland and Africa. I don't have the resources to do that. So I have to confine my sampling to a real area that I actually have available to me, in this case, East Texas. And it's necessary that we make that admission as part of our scientific publication so that other scientists can say, okay, well, this was true in a relatively rural area in East Texas. I wonder if it's also true of people in New York City. I wonder if it's also true of people in rural Utah. I wonder if it's also true of people in Scandinavia. So end up replicating our experiments not only to test and see whether or not we have forgotten something, but whether or not it's true of all populations, right? We also have a self-selection bias. If I was going to pick people, often I would select people who had self-selected. By choosing to take my class, you could have opted also to be a part of a scientific experiment that I was going to do. We refer to this as a self-selection bias, and even if we're going out into the population, into the public, we have a lot of people who choose not to participate in that study. We have a lot of people who choose not to volunteer, and so we have a self-selection bias there as well. Even the Gallup company has a problem with self-selection bias because they're calling people on the phone, and a lot of people don't have time or energy or care to talk to this company on the phone for the 30 to 45 minutes that it takes to engage in their surveys. We can also have pre-screening biases. Now, pre-screening biases are rarely by accident, but if we wanted to study, for instance, brain cancer patients, we would pre-screen our sample to make sure that people actually have brain cancer. It doesn't do us any good to do tests on brain cancer patients on people who don't have brain cancer. So we pre-screen. And all of these biases, and you try and note any biases that you had in your sampling. You note those in your paper so that the other scientists who are reading your paper can note, yes, this person had these biases, and we need to make sure that we replicate so that we can expand beyond these biases and eliminate them through replication. So that's also part of why we publish and replicate our studies. So, when we start looking at understanding what is a sample and what is a population, we can start looking at these. If we look at professional football players, that is a population. 10 students from Harvard University would be a sample. Albino rats is a population, whereas 100 adults over the age of 65 is a sample. And what you start to notice about the pattern here is if you have a limited number of individuals, that's a sample, because that means that you have taken a certain number of individuals and sampled them, whereas something that doesn't have a specific number of individuals is usually a population, because it's almost impossible to count the number of people in a population. That's not necessarily the case. For instance, someone probably knows exactly how many professional football players there are at any given moment. If you wanted to do the math on all the football teams, you could probably do it yourself. It doesn't change very much because there's a specific number of people on each team. However, the number of students at Harvard University may change from semester to semester, even week to week, depending on how many individuals apply and how many individuals drop out and how many are accepted. So we might accept a certain sample of those students. We can break most of our research down into two broad basic portions. We can look at descriptive research and we can look at experimental research. Descriptive research is a method to observe and describe behavior, but what makes it different, what truly makes descriptive research different than experimental research, is that when we do descriptive research, it is not possible to ascribe cause and effect to descriptive research. Whereas with experimental research, we can begin assigning cause and effect relationships to our variables. There are several different types of descriptive research that we can talk about, and we'll talk about each one of these in a little bit more detail. But in that, we can talk about naturalistic observation, we can talk about surveys, case studies, and correlational analyses. So, naturalistic observation is often thought of as systematic people watching. You can do this in a variety of environments. You can do it in the laboratory, as shown here in the picture, but that's usually good for kids. Kids don't necessarily recognize that they're in a laboratory, and so you can look through this two-way mirror and observe the children. Adults are a little bit more savvy and they can tell when they're in a laboratory, and that changes their behavior. The point of naturalistic observation is often to watch people when they don't know they're being watched, to observe natural organic behavior. When people are being watched, they do alter their behavior for a lot of reasons, and we'll talk about some of those reasons a little bit later. But with naturalistic observation, we can study things that are too unethical to do an experiment or are impossible to do in an experiment. For instance, observing smokers. We can't force a certain population to be smokers and another portion of the population not to. So we observe smokers and non-smokers separately, right? So that sort of makes it more along the lines of a naturalistic or along the lines of a correlational analysis, which we'll talk about a little bit more later. The problem is that with naturalistic observation, for instance, sometimes there are things that are too unethical to do naturalistically. For instance, if we were going to be studying sexual practices, we could not study that using naturalistic observation. It would be unethical to be observing people while they're engaging in sexual activity without their knowledge. But with naturalistic observation, we can also observe a lot of things that people might lie about. And that's fairly important. I mean, people lie about things. People lie about, for instance, how much alcohol they take in on any given day. Some of the problems with naturalistic observation is that it's extremely time-consuming. You have to wait for the person to actually engage in the behavior that you want to observe. You can't make them engage in it. We were doing an experiment, for instance, with bathroom soap use, right? And while we could not obviously observe people while they were in the bathroom, that would be unethical. What we can do is observe the level of soap. We can watch how many people go into the bathroom, and we can observe the level of soap at the end of the day. Therefore, being able to determine, on average, how many people are actually using the soap. It's time consuming, and it requires you to essentially sit where you can see the bathroom door all day long. Okay? But we cannot use this method to determine cause and effect. We can only determine that there is a relationship between two variables. Because with naturalistic observation, there are too many other things that we cannot control. Because it's in a naturalistic environment, there are a ton of things that we are unable to control, a ton of things that could be happening that we have no control over. And so we can't determine cause and effect with naturalistic observations. Another method of descriptive research that we can use is surveys, polls, and questionnaires. Simply asking people about their behaviors. And each of these methods uses a slightly different format for it. But there's huge advantages to this. Data collection is extremely quick and relatively cheap. You can test dozens of people at the same time using surveys, polls, and questionnaires. You can sit one or a couple of researchers or research assistants really at a table and just pass out questionnaires to anyone who passes. You expand your sample size and you make things available to everyone. Surveys, polls, and questionnaires are great, particularly when you're using, for instance, social media, where you can actually have people answering your polls and questionnaires from all over the world. There have been several of these that have gone essentially viral within the community, allowing people all over the world to answer questions and to participate in these scientific studies. And in that case, it is particularly cheap, in some cases free, if you're doing polls using, for instance, Facebook and various other online tools. If you're going to send it out with the mail, then surveys, polls, and questionnaires become a little bit more expensive. The thing with this is that if you're going to send them out in the mail, or if you're going to be using phone calls, you can anticipate about a 10% return rate. That is, for every 10 that you send out, you'll get one back. So if you need 500 participants, you'll be sending out 5,000 pieces of mail. And this can get very expensive very quickly. Some of the other disadvantages to this is that people have a tendency to lie, particularly when they think that you might be able to track their answers, even if they don't ever put their name on the paper. Even if there's nothing to identify the participant, they will lie, sometimes to please the researcher, sometimes to make themselves feel better about what they're answering. And a lot of people lie on accident. And that seems sort of ironic, but we actually have what we refer to as the halo effect and the horns effect, where people don't even realize that they're lying about their research. They don't even realize that they're lying about what's going on, because what they're essentially trying to do is subconsciously please the researcher or please themselves. And again, you can't determine cause and effect with these methods. There's too much. All you can do is say that this is what is happening, right? You can describe behavior, but it's very difficult to explain the behavior given simply answers on a survey or questionnaire. Another form of descriptive research that we can use is a case study. This is an intensive study of one person or of a group, and we can study individual groups. The point of a case study is to give an in-depth, close examination of an event or a person or a group that presents a rare or unique opportunity. For instance, with Charles Manson, dozens of case studies were done on Charles Manson. He was, thankfully, unique. There's never been anyone else like Charles Manson, no one else with his abilities. And so all of these case studies were done on him and his ability to get people to do things, horrible things, for him, without ever having to raise a finger. We can do case studies on individual groups that are particularly unique or special. And they're fun to write and they're fun to read. They're very detailed. They can be extremely long. They can be a lot of fun. But it's almost impossible to generalize the results of a case study because we are looking at something that's unique. We are looking at something that's special, something that we can't, by definition, generalize to outside people. And again, there's absolutely no way to establish cause and effect with a case study. And then finally, we can look at a correlational analysis. With a correlational analysis, we're looking at a study of how two things are related to one another, but they're things that we can't directly manipulate. We have to be able to look at, for instance, if we're going to look at smokers, we can't make people smoke and we can't make people not smoke. It's unethical to do so. We can also look at things that it's impossible to determine. We could not take and randomly select this group is going to be male and this group is going to be female. And we can't sort of force them to change genders or to change sexes. And therefore, we use instead a correlational analysis instead of an experiment in those cases. Within a correlation, we can have what we refer to as a positive, negative, or no correlation. If you look here in what the label is study 1, we have what we would call a perfect positive correlation. Now this never ever ever happens. Okay, if you get this, then you have done the math wrong. All right, so this would be a perfect positive 1 correlation. And correlations range from positive 1 to negative 1, with 0 being no correlation at all. This perfect positive correlation never happens because what it means is the more someone does one thing, the more they do another. And while we can absolutely get results like that, it's never perfect because individuals are all different. What you'll see more likely is something like study 2. Although this is an extremely, extremely powerful positive correlation, probably a positive 0.9, which is something that you will very, very rarely get. You're far more likely to get something that looks more like an elongated cloud surrounding an average line, more in the 0.4 to 0.3, 0.5 range. Negative correlations are like, for instance, study 3, where the more you do one thing, the less you do another. For instance, if we were going to look at smoking versus long distance running, chances are the more someone smokes, the less likely they are to do long distance running. And so we have a negative correlation between those two variables. With study 4, we can get a zero or near zero correlation where we're getting perhaps a 0.01 rather than a 0.1, where we have this almost random scatter of items, and that shows that there is no relationship between those variables. Now, it's important to note that with a correlational analysis, you can never give cause and effect relationships, and here's why. This is a graph of the per capita consumption of cheese in the United States and the number of people who die by becoming tangled in their bed sheets. You can see that there's a correlation between these two variables. As one increases, so does the other. But there's actually no relationship between these variables. They're not related to one another. It's purely a coincidence. So while we would have a very high correlation, perhaps even 0.7 or 0.8, there's no actual relationship between them and no cause and effect. Another thing that we look at, for instance, is confounding variables. For instance, we can look at the amount of ice cream consumed in the United States and the number of people who die while drowning. There is a very powerful correlation between these two things, but there's no causation because there's a third variable that we haven't taken into account, and that variable is average daily temperatures. The hotter it is, for instance, during the summer, the more people eat ice cream and the more people go swimming in deep water. Therefore, the more people are drowning during this period of time. And so this presents a strong positive correlation, but it's also irrelevant because of this third confounding variable that links those two and is indeed the cause of both of them in a certain way. An experiment is the last form of research design that we're going to talk about here. And this is the one that you can talk about cause and effect with. Because with an experiment, we can eliminate all the other variables that might confound our study. We can isolate our participants in a way that allows us to remove all of the other distractions and other things that could possibly be happening so that we can examine exactly what causes what. Okay? We can eliminate all these outside influences. On the other hand, by eliminating all of these outside influences, we also make it very difficult to generalize what happens in an experiment to what happens in the outside world. Because the outside world does have all of these external influences on a thing. And so you have to be very careful when you set up an experiment to make sure that you're not necessarily eliminating too much. And so with a psychology experiment, we tend to do experiments primarily in things like classroom settings where most of those outside variables would be eliminated anyway. Sometimes experiments are unethical or impossible to do because of the necessity of manipulating variables. And experiments are very expensive. Renting laboratory space can be hundreds, even thousands of dollars a day. And so we have to write grants and we have to get other people to pay for our research, which is difficult and time consuming. So, if we want to look at which research method we would use, we have to start looking at what method and what exactly we're studying. If we wanted to study, for instance, were serial killers abused as children, likely we would use a case study for that. Okay? We would go and talk to not only the individuals themselves, but their families, their friends. We would look at police reports. We would do a very in-depth study of a few specific, unique individuals to determine whether or not they were actually abused as children. If we wanted to look at what type of students work out on campus, An obvious one might be, for instance, a survey or poll. But what you're going to find there is that a lot of people will lie and say that they are working out when they're actually not. An easier way to do that would be to go to the campus recreational facilities, examine and watch what types of people are working out on campus. So naturalistic observation in that case. Does meditation help to reduce stress? I would use an experiment in that case because you can actually then measure stress levels before and after a period of meditation. So that would work out very well with an experiment. If you wanted to examine which type of drugs helps reduce cholesterol levels, you absolutely need an experiment. There's no other way to do that, really. And if you wanted to look at, do women smile more than men? Personally, I would use a naturalistic observation for that. Going into an environment and watching people and determining who smiles more often. Now, in an experiment, it's often not enough to have just an experimental group. In some cases, it would be. For instance, if we were going to study whether or not meditation reduces stress, having one group would be sufficient because we could measure stress levels, have them meditate for a period of time, and then measure stress levels again. But with many experiments, that's not enough. Instead, we would need a control group. We would need a group of people who are not exposed to your independent variable so that we can measure them both before and after. And then measure another group before, and then have them do the experiment, and then again after, so that we have a baseline of information and determine whether or not your experiment actually produced any results. This is particularly true for experiments that might take a long period of time. When we're doing this, even after we've had random selection of our sample, then we have again a random assignment of individuals within that sample to the groups. Okay? Every member of your sample has an equal opportunity to be assigned to any of the given groups, and you usually will have one control group and at least one, maybe more, experimental groups. Okay? And what we want to happen essentially with random assignment, we want to eliminate as many variables as possible. And instead of having to keep track of all the possible variables that could alter an individual's response to your experiment, instead we randomly assign so that we use chance to eliminate those variables. And what should happen with random assignment is that you get groups that are essentially identical to one another. You get groups that have the same percentages because you have assigned them to the groups at random, therefore producing essentially random groups, right? And therefore hopefully equivalent groups. And if you have a large enough sample, your groups will be equivalent. And so you want groups that, like, you don't just have people who come in the morning or in group A, people who come in the evening have group B, because there's going to be a difference, right? The people who come in the morning are going to be different than the people who come in the evening. So you want randomly half of your people that come in the morning to be in group A and group B. Okay? So we have that random assignment issue so that we eliminate as many biases as possible. Another way to help eliminate bias in your experiment is to use what's referred to as a double-blind procedure. If we were going to test, for instance, these Blimpo pills, all right, we start taking these pills, and but instead of having the researcher go out and say, all right, well, y'all, this group is going to take the Blimpo pills, and this group, you don't get them, we're just going to do the experiment. You don't want to do that because that sets up a whole lot of psychology in, for instance, the control group. They know that they're a control group, and so they may begin behaving differently. It may even affect how their body processes fats. So instead of doing that, you want the researcher to never interact with any of the participants because the researcher knows who's in which group. Okay? The researcher has a list, and they say, all right, this is group A, this is group B. Group A is getting, in this case, we want group A to get a placebo pill, right? That is a sugar pill that they're being told is the real thing. And then group B is getting the real thing. But instead of the researcher interacting with these individuals because he knows who's getting what, he gets his research assistants to give out the pills. And the assistants do not know which pills they're giving out. The assistants are always being told that they're giving out the real pills. That way they don't give any subconscious cues to the research participants about which pills they're getting. This is referred to as a double-blind procedure because the participants are blind, that is, they don't know which pills they're getting. And the assistants that are giving out the pills and collecting the data also don't know which participants are getting which. The researcher does, but the researcher that is not directly involved with the data collection. And what we have also in this is the placebo effect. So there's a group of people, your control group becomes what we refer to as a placebo group. The placebo group does not know that they're not getting a real pill, and so their body will alter a little bit as though they were getting the real pill because they believe that they were. The placebo effect is very powerful, and we've actually had a lot of studies done on the placebo effect and how important it is to include. Now, once we've collected all of our data, we need to make sense of our research results. So we're going to analyze our data using statistics. This is actually a statistical analysis model. You don't need to know it for this class, but this is the model for determining how far away from average an individual is. All right, and we'll talk about exactly what that means here in a moment. Our first step in statistical analysis is to describe the data, and to do that we use descriptive statistics. Two of the most common forms of descriptive statistics is first the mean, which is simply the average. You add up all of your scores and then divide by the number of scores that you have. That gives you the average, and what we refer to as the mean. Okay, that's essentially the center point of your scores. We can also look at the mode, which is the scores that occur the most often. And ideally, the mean and the mode are the same, but not always. Right? You can even have studies that produce what we refer to as a bimodal or a multimodal distribution, where you have several peaks, that is, several modes that show up within your data, but you will always only have one mean. Another way that you can look at your data is a standard deviation, and that model that we looked at on the previous slide, that big, scary-looking equation, is a standard deviation equation. And that shows you how much your participant scores vary from one another, and it tells you how far away any individual score is from the mean. Once we have our descriptive statistics, we start looking at inferential statistics, and this allows us to draw conclusions about the data. Now, if you thought that the equation for standard deviation was big and scary, our inferential statistics equations are way, way worse. And we usually use a computer to do our inferential statistics for us. There are specialized programs that will produce inferential statistics if you enter in all of your data correctly. The most common inferential statistic that we're going to use is a p-value. And a p-value tells you what are the chances that you got your results because of chance. Okay. In general, in psychology, we look for an alpha value. That is, an alpha value is a value that you set to determine whether or not your results are due to chance. And in psychology, we usually use an alpha of 0.05. That is, we are willing to accept that there is a 5% chance that our data was a result of a mistake because of chance. okay, that we've made an error to suggest that there is an effect when there isn't 5% of the time. With some experiments, for instance medical experiments, where our drug may actually harm someone, our alpha value may be much, much smaller, 0.001 for instance in some cases. That is a 1/10 of 1% chance that we've made that mistake. Now with psychology, because most of our experiments are not life-threatening, we can accept a 5% chance of that error. So we set our alpha at 0.05, and we want our p-value to be lower than our alpha value, okay, so that there is a less than 5% chance that we made a mistake. Okay. Now your p-values can be either a relatively simple value or an extremely complex one. For instance, when I was an undergrad, there was a graduate student who had chosen to do what we refer to as a Mankova design, a multiple analysis of covariance. That is, her experiment, her variables, she had so many variables and they were so interlaced with one another that she had to use a mathematical model that was too complex for a computer to do the design. She had to do the experiment, she had to do the math by hand, and she had been working on her equation for 6 months just to do the math. I recommend you do not do a Mankova experiment. It is extremely complex, unless you absolutely have to. In her case, she needed to, and she regretted doing it, but her thesis was also amazing. So, inferential statistics can be very complex or relatively simple and able to do on a computer. When we do experiments of any kind, whether that's descriptive or naturalistic or a true experiment, it's necessary for psychologists to follow ethical guidelines. And while various psychological organizations, in particular the APA, have listed ethical guidelines, it's necessary for each experiment to be checked. And the Institutional Review Board of institutions is considered sort of the ethics police, but they're also the judge and jury. The Institutional Review Board is a set of scientists, an interdisciplinary board, that examines potential experiments to determine whether or not they follow ethical guidelines. There is no institutional review board at Angelina. If you were going to start doing experiments, you have to get it checked. You have to get your experiment checked at the institutional review board at SFA. Okay, and for the most part, most experiments that come across the institutional review board can be taken care of fairly quickly. Right? They don't present any particular threat to your participants, so they can be examined by a smaller board and looked at and approved. If your experiment presents a possible threat to your participants, or if it has to do with children, it requires a full review from the Institutional Review Board, which can actually take several months. There are several ethical guidelines that all experiments with humans have to follow. You have to get, for instance, informed consent. You have to obtain permission from your participant to participate in the study, usually written permission to participate in your study. And in order to do this, it has to be not just consent, but informed consent. Your participant has to know what the study's about, what you're looking for, what sort of thing they're going to be doing. They have to know what the risks and benefits of their participation actually are. Now, occasionally we have to lie to our participants. We have to deceive them concerning their consent, concerning what the experiment is about. If you're going to do that, the IRB must approve that deception. The IRB must approve the necessity of deceiving your participants. Okay? So that has to go through the Institutional Review Board as well. With children, children cannot give consent. You have to get informed consent from the parent and then assent from the child. That means you have to go through 2 steps, and it's very difficult to get consent and assent for a child to participate in a study. It can be done, and in a lot of cases it's necessary, but it's much easier to get consent if you're dealing only with adults. We must protect our participants from harm and discomfort to the best of our ability. And we must protect confidentiality. And there's two ways that we can protect the confidentiality of our participants. We can have either a confidential or an anonymous research. With confidential research, you know who your participants are. You actually have a list of their names. And with confidential research, their names are tied usually to a serial number or some other identifier, so that you can discuss your participants without revealing their names or identities. That's confidential research. And it's necessary in cases, for instance, like drug research, where you might have a placebo group, but if the drug works, you need to be able to offer the real drug to the placebo group, so you need a record of who is who. With a lot of experiments, particularly one-off experiments where they're going to come in for one day, do the experiment, and then leave, we can use anonymous research, where you simply never collect their name. That's infinitely easier. Using anonymous research where you never collect their name absolutely helps. And then you have to provide a complete debriefing, particularly if you have deceived your participants in the beginning. After the experiment, it's necessary to talk about how you deceived them and what sort of research was actually being done and what they actually did. You also tell them how they can contact you to get the results of your study and to see what actually happened. Now, in all honesty, most participants never contact the researcher to determine what experiment was actually being done and what the results were. Usually they lose their debriefing packet long before they would be able to ask about the results of the experiment. If working with children is hard, working with animals is far more difficult. You can't simply go to the IRB if you're going to work with animals. Instead, you have to go to the Institutional Animal Care and Use Committee, the IACUC. This approves and denies permission for studies involving animals. If you're going to use animals, you cannot go to the SFA IRB. You instead have to go to either the Texas A&M or the Texas Tech IACUC. SFA does not have an Animal Care and Use Committee. It also doesn't have the facilities necessary to take care of the animals that you're using in your research. You have to do an enormous amount of paperwork proving that you're protecting the animals from pain and that there's no alternative, that you could not do your experiment on humans. You also have to prove the clinical and scientific merit of the study, and this is particularly true if you have to terminate the animals at the end of the experiment. I worked for a while at LSU Medical Health Center in Shreveport for a researcher who was doing cancer studies on rats. And to give you an example of how intense it's necessary to work with the IACUC, he had to start designing his experiments 2 years in advance in order to get approval through the IACUC at that facility. It was also necessary, if you were going to work with these animals, you had to go up to the top floor of the building, go across the building, scan a key card to get into a closet where there was an elevator. The elevator only went between the 8th and 9th floors. It was the only way to get to the 9th floor also. So you had to go into the elevator, turn a key, access the 9th floor, then scan your key card to get back out into the hallway on the 9th floor. Scan your key card to get into the individual rooms where the animals were being held, and then do the whole thing in reverse to get out. Every room had its own dedicated air conditioning units. It had its own air handlers. It had its own dedicated food production facilities. It had its own dedicated bedding production facilities. It had its own dedicated water purification facilities. The animals were very carefully taken care of and isolated with no windows and absolute environmental controls. And it's absolutely necessary because organizations like PETA, the People for the Ethical Treatment of Animals, have been known to bomb facilities in order to rescue the animals involved. And of course, they end up killing the animals as well as a number of people inside the facilities when they do that. It's absolutely necessary. In addition, the animals have to be protected from the environment because a lot of these animals are bred, for instance, to have no immune systems, or they're in a situation where exposure to the environment could corrupt the information in the experiment. So getting information through the IACUC is very difficult. And very time consuming, and you have to absolutely know that there's no other way you could do the experiment. It's much easier to do experiments on humans. So we don't do experiments on animals lightly at all. It's never done without extremely good reason. So that's our look at psychology as a science. Hopefully you followed all of that. You can of course go back and look at it again. And for next time we'll do chapter 3.